Good morning, everyone. Today I would like to start with the introduction. Machining operations play an important role in shaping, cutting, and finishing materials in the manufacturing industry. So each machining method has its own purpose, tool movement, workpiece motion, and level of surface finish. Because every operation produces different outcomes, comparing them helps us understand how they work and when they should be used. And this comparison also allows us to choose the most suitable machining process for specific parts or product requirements. Grooving is mainly used to create narrow recessed channels on a workpiece. This is important because these channels serve specific functions during manufacturing. It is also used to provide seats for O-rings, snap rings, and seals, so grooving helps ensure that these components can fit properly and stay in place during operation. In addition, grooving can reduce material or add stress relief features. This means it can help manage material thickness and reduce internal stresses in a part. Overall, grooving is used to control fit, assembly, and functional performance, so it plays an essential role in ensuring that parts function as intended. Next, for the types of grooving operations, we have single cut grooving, roughing wide grooves, and multiple grooving. These methods are selected depending on the size of the groove and the required accuracy. Next, I will explain the tool motion. For tool motion, the tool feeds radially inward to cut the groove. This means the cutting tool moves directly towards the center of the workpiece to form the groove. The tool may also move axially to control the groove width, so this movement helps achieve the required groove dimensions. And because grooving requires accuracy, it requires slow, precise feeding for accuracy to ensure the groove is clean and consistent. Now, moving on to the workpiece motion. In turning, the workpiece rotates, while the tool stays fixed except for feeding, so the cutting tool does not spin, it only moves slowly to shape the groove. In milling, the cutting tool rotates, and the workpiece stays fixed or moves linearly. This means the movement depends on the type of milling operation used. Next, I will talk about the surface finish. For grooving, the surface finish produces a smooth, narrow channel. There may be fine tool marks present, but they are still acceptable for sealing surfaces, so overall, the finish is suitable for functional and assembly requirements. Now, moving on to the application, here are some example products and their functions. First, the O-ring sealing groove, which is commonly found in a hydraulic cylinder. It creates a sealed channel for O-rings to prevent oil leakage. Next, we have the retaining or snap ring groove, which is used on a shaft in a motor or gearbox. This groove holds bearings or gears in position using a snap ring. Lastly, there is the circlip groove for pin retention, found in an engine piston. This groove secures the piston pin using a circlip to prevent axial movement. Now, I will move on to the next machining operation, which is knurling. 1. Purpose. Knurling is performed to create a rough, patterned texture on a cylindrical surface. It is mainly used to improve grip or friction for hands or tools. It is also used to allow press-fit assembly between components, and sometimes to produce decorative patterns. 2. Tool motion. For tool motion, the knurling tool does not rotate by itself. Instead, it moves linearly along the lathe while pressed against the workpiece, and the pattern is formed as the tool rolls on the spinning workpiece. Next, I will explain the workpiece motion. The workpiece rotates on the lathe spindle. This rotation causes the knurling tool wheels to roll and press the pattern onto the surface. So, the pattern is formed mainly because of the spinning motion of the workpiece. Now, moving on to the surface finish. Knurling produces a rough and textured surface. It forms regular patterns such as straight lines, diagonal lines, and cross-hatch or diamond patterns. Overall, the surface feels non-slip and easy to grip. Knurling is commonly used when a stronger, non-slip grip is needed. It creates a textured surface that makes the product easier and safer to hold. Applications. 1. Hand grip enhancement. Knurling increases friction on tool handles so users can hold them firmly without slipping. 2. Manual tightening components. Parts that are turned by hand use knurling so the user can tighten or loosen them easily. 3. Fitness and sports equipment. Gym equipment often gets sweaty. Knurling helps ensure the user maintains a secure grip. 4. Decorative purposes. Some products use knurling for a stylish or professional appearance in addition to grip. 5. Tool and machine controls. Knurled surfaces help operators safely adjust levers or handles, even with oily hands. Example products: screwdriver handles. The knurled texture prevents slipping and helps apply more turning force. Thumb screws, designed to be turned using fingers only. Knurling gives better friction for tightening. Dumbbells, handles are knurled so they won't slip from the user's hands during exercise. Flashlight bodies. Knurling ensures the flashlight stays secure even in wet or outdoor conditions. Lathe machine handles. Machine operators can grip the handles safely, reducing the chance of accidents. Machining operations are very important in the manufacturing industry because they help us shape, cut, and finish different materials to meet specific product needs. Each machining method has its own unique purpose, tool movement, workpiece motion, and the type of surface finish it can produce. These differences mean that every process is suitable for different kinds of tasks. By comparing these machining operations, we can clearly understand how they work, what results they produce, and which one is most suitable for a given situation. This comparison also helps engineers and operators make better decisions when choosing the right machining process for a specific part, ensuring better quality, efficiency, and performance.